All right, so we just finished talking about your basic intermolecular forces, your van der Waals, your dipole-dipole, and also your hydrogen bonding. And now we're going to talk about some various properties of liquid. You could think of it as liquid behavior also. Things like vapor pressure, boiling point, surface tension, and something called viscosity. And intermolecular forces, as we have now been introduced to, will explain them all, and it'll be very exciting. By the way, don't you enjoy the background of this slideshow? Properties of liquids, water droplets. We're actually going to talk quite a lot about water droplets. It'll be pretty awesome. All right, so no animation on this slide. Sorry about that. So intermolecular forces, as I had just said, explain properties of liquids. First off, vapor pressure. What the heck is vapor pressure? It is a pressure exerted by a vapor held above a liquid. Okay, think about a water bottle that you've drank half the water out of the bottle, and there's a lot of air at the top of that bottle. The water that's in the bottom will actually volatilize. It will move from the liquid and into the gas phase in the what's called head space or air space above the liquid within the bottle. That is vapor pressure. So you might not think it's not intensely pressurized, that bottle of water, but it does have some pressure that builds up on the inside because of water droplets vaporizing and becoming little molecules of water gas in the area of the water, or in the area of the gas above the water below it. So pressure exerted by the vapor held above a liquid. It depends on the ability of the liquid molecules to escape the liquid and become a gas. In other words, if the liquid is not able to get up out of the liquid and become a gas, then obviously your vapor pressure is not going to be very high. These liquid molecules will be more likely to escape if intermolecular forces are low. So something like water, which by the way is going to have van der Waals, it's going to have London dispersion forces because it's a molecule. It has dipole-dipole because it is a polar molecule, but it also has hydrogens bonded to oxygens, which means it has hydrogen bonding. So strong intermolecular forces, I'd say, and that means that water has actually a low vapor pressure, meaning that it's very hard for the liquid to become a gas and to fill the space above the water and pressurize that bottle. However, if you have something that is a very volatile liquid, something that's able to really evaporate easily, it can pressurize the inside of a bottle relatively quickly, and that would be a higher vapor pressure. Boiling point, I know that you know what it is, but when you look at the exact same ideas that we just talked about for the same reasons above, if you have weak intermolecular forces, meaning that your molecules are not held very tightly together, you're going to have a very low boiling point, which means that the liquid boils faster. So the more intermolecular forces you have, the higher your boiling point will be, because you have to put enough energy into that system, into those molecules, to break the hydrogen bonds, to break the dipole-dipole interactions and the London dispersion forces. And all of that extra energy means that you're going to have to raise the temperature higher to get it to boil. So between looking at properties of vapor pressure and boiling point, hopefully you can see that, again, intermolecular forces really is where it's at. It explains everything. To talk then about surface tension. Surface tension is kind of an interesting thing. I know that you've heard of surface tension before. If you had me in biology, we do talk about it pretty much a lot. But when you think about molecules in the body of a liquid, so again, think about that water bottle we were just talking about, and imagine that you're looking at the dead center water molecules on the inside of that bottle. They have, as this picture is showing, if each of these green molecules is a water molecule, and this is a little bond kind of intermolecular attraction holding them together, they actually experience equal pull from all sides. And that's within the body of the liquid. But when you look at the surface of the liquid, do you notice in my second picture here that I've created a surface, which is this line here, but then I've also shortened these intermolecular attraction lines, and I've drawn the individual water molecules much closer together. They don't end up having equal pull, and what that does is it actually tightens those molecules together to create what's called surface tension. Surface tension it will draw the surface molecules toward the body. So it literally will pull the water molecules that are next to the surface closer and down and in, and it basically tightens them. This results in the least amount of surface area being exposed. And this is actually an explanation for why when you drop water on a desk or something, it doesn't form a square or just spread out into infinity, but it forms a little droplet. So that little droplet actually creates the least amount of surface area. And again, it forms tension on that surface because those water molecules are being drawn close. So the actual definition for surface tension is the tendency of a liquid to resist an increase in surface area. Oil does not have surface tension like water does. If you ever have dripped a drop of oil on a counter, it forms a droplet, yes, but it's a much flatter drop. When you talk about a drop of water, you can get a drop of water to be pretty tall. In fact, if you had me in biology, we took some time and we dripped drops of water on the surface of a penny. And it's amazing how piled up those drops can get to form this incredibly large domed surface. If you try to do that with oil, it will not work quite the same. So surface tension is something that, again, with increased intermolecular forces, you're going to have increased surface tension. There is a measure for it. We won't deal with it a whole lot, but it's measured in joules per meter squared. And the more polar the molecule is, the stronger the surface tension. So again, this is a water molecule. We know that it has London dispersion, it has dipole-dipole, and it has hydrogen bonding. So that makes its surface tension very high. In fact, it's one of the highest on the planet. Whereas oil, which is it doesn't tend to be a polar molecule, so it just has some London dispersion forces, it's going to have very low surface tension. Excuse me. Another thing in terms of surface tension, and this is actually something that, again, if you had me in biology, we did this. Surface tension is affected by dissolved substances. So for instance, when we were in biology, we took the water and then we added salt to it. And the salt water actually will not hang on the penny quite as long because of a disruption of surface tension. So soaps and detergents are actually one of the best ones to talk about with this. Soaps and detergents are nonpolar. And so what they do is they actually get in between water molecules and they cause the intermolecular attractions of the water to be drastically reduced. So when I say of the solvent to be drastically reduced, I'm talking about the actual water. And so if the intermolecular attractions of the water are reduced, then you're going to have much lower surface tension, which means it won't stick together in droplets quite as well. Another factor that goes along with surface tension too is something called capillary action or capillary rise. In fact, in your gases lab that will be coming up here shortly, capillary rise is something you're going to have to measure to make sure that you have a correlation, basically like a correction factor. Because what capillary action is, it's something you can't stop. It's a spontaneous rising of a liquid in a narrow tube. So what you're actually going to have in the lab when we do this lab is a thin glass tube, and water will be at the base of the tube, and water will actually just sort of pop right up into that glass tube higher than the liquid level around it, which is pretty crazy. Why does this happen? Well, it results from an attraction of the liquid molecules to the oxygen atoms in the glass. Glass is silicon dioxide, and so when you have liquid water attracting to glass, that's two different compounds attracting. That's called adhesion. And then there is additionally cohesion that's happening because when the water atoms attract to the glass, continuing on, there's a subsequent pull on other molecules. It's kind of like a train of water molecules. So when the first water molecule is pulled, the rest of the hydrogen or the rest of the water molecule train, all these little cars kind of pull along also. And then the water itself will be drawn upward and into that capillary or tube. The word capillary, it certainly applies to biology. The smallest blood vessels that we have in our skin are called capillaries. In chemistry, a capillary is just considered a very thin tube, which is basically what your blood vessel capillaries are. So anyway, if another way to maybe think or visualize about this, if you ever had one of those little trains when you were a kid that has a magnet on the front and the back of each little train car, a little wooden train. If you attach all the magnets, all you have to do is pull the first train car, and the rest of the train cars come right along with it. And each train car in this analogy are the water molecules, and they just pull right along. And that's how they rise up. So to give you just a picture of how that looks, you can see here on the left side, this is what it actually will look like. So you can see the capillary, the thin tube. You can see that there's water beneath it. And notice that the water level in the beaker here is way lower than the water level in the tube, and that is capillary action. Also, what capillary action causes is a meniscus. So in the picture that you see there, the blown up one where my cursor is now, that's a typical meniscus for water. The water meniscus will curve downward. It is a concave meniscus. And let's make sure, too, that we're clear that when you would measure this in something like a graduated cylinder, that you measure from the bottom of the meniscus. So if there was a line right about there, that's where the measurement would actually have to occur to be a proper measurement. Now, I want you to notice next door here, we've got mercury. And notice that this looks really different. In fact, in this case, the mercury cannot even get up the tube to the level of the mercury within the beaker. And also notice that the meniscus is completely opposite. It's a convex meniscus in this case. And this is all because of the nature of the water and the mercury themselves. So this is capillary action of water. The water meniscus is concave because water has a greater attraction to the glass than to itself, which is another reason that sort of explains why it draws up the glass, because it's very, very attracted to the glass. The mercury, on the other hand, is convex because the mercury, being metal, it's just liquid metal, actually has a greater attraction to itself than the glass. Hence, it doesn't want to go up the tube. It wants to stay with its home, with its people. And so we get a completely different meniscus look, which is just sort of an interesting thing. The majority of the things that you guys are going to work with will be water-based, and so you will always see a concave meniscus, understanding that the picture on the left is what you are likely to see with anything that we do in this class. So that's surface tension. Next and finally, we're going to talk about viscosity. Viscosity is a measure. It is actually a quantitative measure also, but it's a measure of a liquid's resistance to flow. So when you say that something is viscous, it means that it's thick and syrupy, and when you pour it, it takes a while to pour. Honey is very viscous. Water is considered to essentially have no viscosity. It doesn't resist flow. If you pour a cup of water, it will make the water go everywhere. The water's not going to stay in the cup, which would be kind of cool if it did, but it won't. So measured by the time it takes for the liquid to flow through a capillary tube, which you now know is a thin glass tube, or by the time it takes for a steel ball to fall through the liquid. Okay, so those are kind of interesting ways. We pour it down a tube and time it, or let a steel ball fall through it, or I used to work in a chemistry lab, and we tested industrial gigantic batches of soap, and they had specifications for certain viscosities. And so what we used in the chemistry lab that I worked in was called a viscometer. I could almost pronounce it. And the viscometer was kind of interesting. You put the soap in a really, really big test tube. And then you had these metal probes that you would put down into it, and then the probe would turn within the liquid. And so however fast the probe was turning, that would then tell you an actual measurement for viscosity, which was kind of cool. The easiest way, though, to determine viscosity is simply just making a visual observation. Like, of course, if you have syrup versus water, you recognize that one of them is way thicker than the other, and the thick one, again, is called viscous. Another thing that will impact viscosity, or one thing that impacts viscosity, is temperature. For instance, if you decrease the temperature, you will increase viscosity. Please think about syrup or honey or anything like that. Hot honey versus cold honey, or hot syrup versus cold syrup. If you're one of those families that takes your syrup and puts it in the microwave, you'll recognize it gets a lot thinner and that is becoming less viscous. So temperature, it begins to make molecules move faster, and they don't stick together as well, and that leads to less viscosity. So you see a lot of connections to things that we've learned about and talked about, all coming together in terms of chemical behavior. So the final thing that we want to talk about is I want to make sure that we kind of have a full explanation here about how these intermolecular forces affect properties. So again, surface tension. Another thing that can actually happen with surface tension is that it can increase with increasing intermolecular forces. Okay, I guess that's not another thing. That's the same thing we talked about. This also tends to mean that generally higher molecular weight compounds will have higher surface tensions because there's more electrons interacting, right? So more electrons mean more London dispersion forces, which means increasing intermolecular forces, which would lead to increased surface tension. Now, of course, not being aware of hydrogen bonding would be a major issue at this point, because water, for instance, it only has a molecular mass of 18, yet it has incredibly high surface tension, and that's because of hydrogen bonding. So when you're comparing two compounds with similar intermolecular forces, like if they're both nonpolar compounds, for instance, then the higher molecular weight would have more surface tension. So you want to consider these in categories. You have to consider nonpolar molecules together and polar molecules together, and then hydrogen bonding molecules will get considered together also. And then another thing about viscosity, it depends only partly on intermolecular forces. Ooh, that's interesting. So we do know that increasing intermolecular forces will definitely increase viscosity. However, this last bullet point is really important too. Viscosity can also be affected by the length of the molecule, because if you're longer, you can get tangled. That makes sense. You know, if you think about having an incredibly long string, like 6 feet long, and let's say you're just gonna have that string and you're going to drag it everywhere you go, chances are good you're going to get at least a knot within that string if you just drag it with you everywhere you go. Throw it into your purse, gentlemen, maybe your wallet. That 6 foot long piece of string is very highly likely to get tangled. But if your string is only an inch long, getting your inch long string tangled is much harder. So again, longer molecules become more tangled, and that's really what leads to viscosity, which is that stickiness to itself. So this is a presentation to me that really opens up a lot of information about how intermolecular forces affect chemical behavior. And again, this, guys, is why it's in your summer assignment. So again, I ask that you really make sure that you understand this. Go back and look at the information you did in your summer assignment and make sure that you had a good understanding then, and if you didn't, that you've made some corrections. But again, stressing, so important, so important, so important, okay? So we'll come back to class tomorrow. We'll talk some homework, and it'll be a great day. Yippee, yippee.